centimeter equals to 1 liter.
Please mute yourself.
Sir, এটা তো হচ্ছে decimeter. 1000
Hello.
cubic centimeter equals to 1 cubic decimeter.
Hello. Greetings, everyone. Since it's already 5, let us begin our today's live session number 9. So this course, as we know, is being taught by Professor Sanjeev Sambadan, and we regularly solve the assignment questions during these live sessions. So today we will be having some questions related to BJTs. So in here, it states that we have been given some parameters for an NPN BJT with the Dn equal to 20 centimeter square per second and NB naught is equal to 10 to the power 4. So this should be 10 to the power 4 per centimeter cube. Let me write it clearly, 10 to the power of 4 per centimeter cube, and the area is 10 to the power minus 4 centimeter square. The base width is given to be equal to 1 micron. So the base width is given to be equal to 1 micron, and we have been told to calculate the collector current when we have some base to emitter voltage applied, which is given to be equal to 0.6 volts. So this collector base junction is reverse biased, and we have been told to find the collector current assuming the thermal voltage to be equal to 26 millivolts. So this transistor is in forward active mode. Uh, so let us write down the expression for the collector current that we have seen. This is the collector current, IC collector current. It is given by Q times ABE, where this is the area of the base emitter. So multiplied by the intrinsic carrier concentration into the diffusion constant divided by the depletion base width, sorry, this is the base width, not the depletion base width, and multiplied by the carrier concentrations, and this whole will be multiplied by exponential of QVB by KT minus 1. Now what we require, since we require this collector current to be found, we need to see what values are present. Since this NB naught is given and we know this NB naught is equal to Ni square by NaB, which is the minority carrier concentration in base. Minority carrier concentration in base. So if I replace by this Ni square by NaB by this quantity, this thing over here, I will get the reduced expression for this collector current to be equal to Q times ABE dN, and this will be NB naught by XP, where this XP is the base width, by multiplied by exponential of QVBE by KT minus 1. Let's add some slides. So now in this expression, we know almost all the quantities. This Q is 1.6 into 10 raised power minus 19, and NB naught is 10 to the power of 4 centimeter cube, and this ABE is equal to the 10 to the power minus 4 centimeter square, and dN is 20 centimeter square per second. 20 centimeter square per second. Let us put these values in this expression, where we have this base width as well. This is 1 micron, which implies 1 micrometer. So we will write these values. This is 1.6 into 10 raised power minus 19 for the electronic charge. For the area, it is 10 to the power of minus 4. For NB naught and Dn, it's 20 for Dn, and for NB naught, it's 10 to the power of 4. This whole will be divided by 1 micrometer, which in centimeter will be 10 to the power of minus 4 centimeter. Since we are dealing in centimeters, we have to convert the micrometer into centimeter, and this will be multiplied by exponential of QVBE by KT. Since this VBE is zero point 0.6 volt, we can write it to be 600 millivolt divided by 26 millivolt. So that millivolt and millivolt will go, and this is minus 1. Now let us solve this expression on our calculator and check the values. So it comes out to be equal to, let me write it down over here, 33.6 into 10 raised power minus 5 amperes, or if I convert it into milliamperes, it will be 0.336 milliamperes. So we have got the collector current, and option B seems to be the right option to go with. So option B is the correct option to go with. Now we have been given in this second question that we have been given some transport factor for the BJT, which is given in terms of the cosh, and this it is given to be equal to alpha t is 1 by cosh of XB by LB, where this XB is the base width and LB is the minority carrier diffusion length. So it will depend on the carrier lifetime, this minority carrier lifetime. And we have been told to find the base width, that's we require this XB this XB to be found in this PNP BJT, so that we will be having the transport factor equal to 0.9967, and this diffusion coefficient is given to be equal to 10 centimeter square per second, and the minority carrier lifetime is 10 power minus 7. So if we go by this, we have to satisfy this alpha t is given by cosh of this base width by the diffusion carrier length in the base. And if I now uh, take the value for this alpha t, which is given to be equal to 0.9967, I will be having 0.9967 is equal to 1 by cosh of xb by lb. Now if I now insert some slide first and take the cosh inverse of this quantity 1 by 0.9967, I should get the value for the xb by lb, that is equal to 0.0814. Now I have the value of the ratio. I require now this diffusion length. This diffusion length is dependent on the minority carrier lifetime and the diffusion constant, which will be dB in this case, and TB, that is the minority carrier lifetime of this base, and that is 10 centimeter square per second for dB, and for this tau b it is 10 to the power minus 7. So this LB will simply be 10 into 10 raised power minus 7, or this will simply be 10 to the power minus 3 centimeter. Now since we require this in this XB by LB to be equal to 0.0814 into 10 raised power minus 3 centimeter. Yes, this LB is 10 raised power minus 3 centimeter. So XB is this quantity, or if I convert it into meters, it will simply be 0.0814 into 10 to the power minus 5 meter, or if I convert it into micrometer, it will simply be 0.81 micrometers. This will be the base width. So this option A seems to be the correct option, and we should go with this option. Now there is another problem which states that we have been given the base current for a BJT which is in active mode, and it is given to be equal to 6 microamperes, and the collector current for the same is given to be equal to 510 microamperes. Now we have been told to find the value of alpha for the same. Wait a second. Okay. So we have been told to find the value of alpha for the same. Now in this problem we have this IC equal to 510 microamperes, and we have this IB that is equal to 6 microamperes. Now this beta is given by, as we know, it is given by IC by IB. So if I just divide these two, 510 microampere divided by 6, I should get the value. So let me do that. 510 divided by 6, it comes out to be equal to 85. Now this alpha is given by beta divided by 1 plus beta. So it will simply be 85 divided by 85 plus 1. So it is 85 divided by 86. It will come out to be 0.988. So it comes out to be equal to 0.988. So we will go with option C. Now let's move to another problem. In this problem, it says that which of the following in the BJT is heavily doped? And I know you will be knowing this answer, and it is the emitter which is heavily doped, because so this is the simple problem. This emitter is always heavily doped. Now there is another problem. These are some straightforward problems. It says that if we are having a BJT where we have been given some statements about this BJT, it is stated that for option A, we have to find the which of the following statements are true. It states that this base width must be designed to be much larger than minority carrier diffusion lifetime. So if we think logically about this, if this base width is much greater than the minority carrier lifetime for these diffusion length, if for example in PNP we will be having this recombination in that base region, it would mean this base region is recombining more and more carriers, that is holes in case of PNP in this N region, and so that we will be getting less number of carriers at our collector. So this option A seems to be the wrong option to select, and option B is just the opposite of this one, and this means that if option A is wrong, clearly option B will be correct. But option C, it's in that it mentions that base region should be heavily doped, and we know that this base and emitter this in this base emitter and collector, always this emitter region is highly doped, and this because we have to reverse bias our base collector junction, and this base is always less doped as compared to the emitter. So as this reason over here also states that we have the diffusion length. This diffusion length is the average distance traveled by the minority carrier before recombining. So since we want this recombination to be minimum in this base region, so we generally design the base width less than this diffusion length of minority carriers, so that there are less chances of recombination. This kind of concepts are today also used if we see the future devices, or when we have short channel lengths, where we see that we are going into the nanometer scale much. Even we have seen the experimental papers going up to 1 nanometer scale as channel length. So this one nanometer device, in that the transport will be ballistic. This there will be very less number of collisions because of this less number of particles being less number of diffusion length, because this there will be no carriers that will be hampering the motion of the electrons or holes, whatever may be the carriers in that particular device. Because we generally see whenever we have some device, we generally say that if it is n type has good mobility. This is general misconception. This is valid if we have devices like silicon, because in that the mobility of holes is much less than the mobility of electrons, and in that case we always see that these NFETs are faster devices. But that is not the case with every material. There are large number of materials that are being investigated currently, and the active research of field that is two-dimensional materials, if we see that the materials like MoSi2N4, that's one such example. It has the holes which are much mobile as compared to the electrons. So it all depends on the effective masses of these materials. How this, not precisely on the effective masses, how this EK will look like, this band diagram. So this effective mass, everything is property of a material. Now let's move towards another statement. It states that what is the early voltage, and as we have already seen these things in our lectures, that this early voltage just represents this interpolated voltage that we get from the IC versus VCE, and this voltage is obtained when we have zero collector current value. So this option, we will go with option C simply. Now let's move towards another statement. It states that if we have this base width modulation in a BJT, what would happen to the conductance? Because as we can clearly see, wait a second, let me put it on silent. Okay. So if we see this IC versus VCE, this this is due to the base width modulation. As we know, this base will change with the bias. This we have already seen in PN junctions how this this depletion width changes with the bias. So this base will not be having the same width because of this depletion change. So we can see this, as it has been clearly mentioned over here, that from a figure, as we see this BJT is, which is an active mode, this R naught is the output impedance or output resistance. So as this base width modulation increases, this slope will increase, which in turn would result in the increase in the output conductance. So this is simple, and we will select the option A. This is the base width modulation, effect of the base width modulation. So there is now other problem regarding this BJT. It says that we have to consider a uniformly doped BJT that is having these specifications, where this base width is given to be equal to 0.5 micrometer, and the doping for this base region is 10 to the power of 6, and similarly, this we have been told to assume this VBI is much less than this applied bias of punch through voltage, that is 25 volts. This should be actually VBI. This shouldn't be, this should be in subscript. So this should be VBI should much less than 25 volts. So it states that we have to find the collector doping. So the punch through has occurred. Let us draw a representative band, what we can say, not a band diagram. Let us draw some visualization of these P and N regions by just drawing this depletion widths in them. So if this is our some BJT, where this is the emitter, this will be its emitter side having the depletion width, and this will be the base depletion width
from the emitter side, and we will be having another interface where this will be the collector side and this will be the base side. And if this is the depletion width on the collector side and this is on the base side, on this base collector junction, let us note it by x1, and this is the total base width, this WB. Starting from here, if this is the WB, this base width of equal to 0.5 micrometer. So we know this space charge region will extend into the base and also into the collector. Now let us denote these dopings on the collector side by Nc and on the base by Nb. Since we require the doping on the collector side to be found out, we will simply use the formula for this depletion width, and it will simply be equal to x1 on the base side will simply be equal to 2 times epsilon naught epsilon r VBI plus this punch through voltage. Since it has been told to ignore the VBI, let's ignore it from right away. So this will be V some VR, that is the punch through voltage, divided by Q multiplied by NC by NB into 1 by NC plus NB. So if this now punch through has occurred, we have to take this VR to be equal to V punch through V punch through, where this punch through voltage is equal to 25 volts. Let us add some slide. Wait a second. Okay. Now we know the values for these almost all the quantities except the uh, this what we can say except this NC, because x1 this punch through will occur when these two, the junction from the emitter side and the junction from the base the collector side, they both will touch each other, because at that time the base would have gone, there will be nothing like the base. So this, if I take this base now equal to the depletion width on this collector base junction side, this is what would have happened at the punch through. So at the punch through, let me replace this x1 by WB and write this as 2 times epsilon naught epsilon r, and also square this because it was in square root, and square this VR divided by Q times NC by NB divided by 1 plus NC plus NB. So this NC could be found to be equal to, if I now solve for this by writing the values for the NC, it will simply be equal to, where this VR is this VPT, this will be WB square, and this WB square was equal to 0.5 micrometers, that is 0.5 into 10 raised per minus 6 or 0.5 into 10 raised per minus 4 centimeter. It is 0.5 into 10 raised per minus 4 centimeter. So let me put it like that, and it is 2 times the epsilon naught, and this epsilon naught let us take it to be equal to uh, 3.9 into 8.85 divided by 1.6 into 10 raised per minus 19. Okay, since we have to take for the material that is silicon, let us take this to be equal to the dielectric constant for the silicon material, not the oxide. So this, since this will be as 11.7, and 10 to the power minus 14, where this Nc is not given and Nb was given to be equal to, this Nb was given to be equal to 10 to the power 16. Okay, 10 to the power of 16, and now 1 by Nc will remain there plus 10 to the power of 16. Let us solve this expression and check its value. So it comes out to be approximately equal to, this Nc will come out to be equal to 8.8, sorry, 8.38 into 10 raised power 14 centimeter cube. So this is option A, that is matching with our calculations. So we will go with this option. Now it has been told in this region to find the depletion width of the collector region. Now I think it should be simple, and you should be able to do this by just writing the x21, that is the depletion width on this collector side. Then let me denote this at the breakthrough. When this punch through has occurred, when a punch through has occurred, and this will be equal to the same formula that will be using epsilon naught epsilon r VBI plus VR. Let us ignore this VBI since it has been given to be ignored. Let me write this directly, this V punch through divided into NB by NC by Q divided by 1 by NC plus 1 by NB. I think I should not solve this. I should keep it like this because it will just be some calculations that you require to do. So let us move towards another problem which says that we have a uniformly doped NPN silicon BJT where this temperature for this operation is going to be equal to 300 Kelvin, and the bias is such that we have this in a forward active mode, and this VCB, this collector to base voltage, is going to be equal to 3 volts, and this base width is going to be equal to 1.1 micrometers. Now we have been given some concentrations, doping concentrations for this that is of the order of 10 to the power 17 for the emitter, 10 to the power 16 for the base, and 10 to the power 15 for this collector. Now we have been told to find the base emitter voltage such that the minority carrier concentration at x equal to 0 is 10% of the majority carrier concentration. So this x equal to 0 is that junction. Now if we see this thing, this is simply, we know that, and this np naught, this concentration of electrons, will simply be given by Ni square by Nb. This is in p side, that is the p part, that is the base part. It will be given by Ni square by Nb, and this Ni square by Nb, if I just put the values for the Ni square and Nb is equal to 10 to the power 16, I should get Ni square by Nb, I should get it to be equal to 2.25 into 10 to the power of 4 per centimeter cube. So Ni square, yes, it will be correct, divided by, okay, yes, it is correct. Yes. So I thought I might have done something wrong. No, I have done it correctly. Uh, I have taken the Ni squared, Ni to be equal to 1.5 into 10 to the power 10, and this Np naught will be equal to this 2.25 into 10 to the power 4. Now at this x equal to 0, this concentration will be given by this Np naught, and this multiplied by this Np naught, this equilibrium concentration Np0, exponential of q VBE by kT. That is similarly the thermal voltage division. So Np naught is given to be equal to uh, 2.25, and we have been told to find the condition that when it is 10% of this concentration. So it has to be the 10% of 10 to the power of 16, that is it has to be equal to 10% of this majority hole concentration. 10% of this majority hole concentration will simply be 10 to the power of 15 centimeter cube. This will be equal to 2.25 into 10 to the power of 4. This will be exponential of VBE by 26. Let us take this 26 millivolts. So now if I do the required calculations, I should get this to be equal to, divided by, 10 to the power of 4 into 0.026, and it should come out to be equal to, this VBI should come out to be equal to 0.63 volts. So if I check this expression with the above, it is the option A, that is matching. So now let's move towards the another assignment. It is the assignment 8. It says that we have to deal with now the MOS cap. So it says that we have some CV curve that has been given, where this V is the applied bias on the gate, this VG. So this CV curve is for the ideal NMOS circuit, NMOS cap. So this has been subjected to uh, what we say high frequency, and at the simultaneous time it has been subjected to the uh, large or fast DC sweep. So it has been put to two conditions, stringent conditions, where the minority carriers will not be given the time to respond, because there will be, first of all, there is high frequency, so these minority carriers will not get the enough time, and also we are having this fast DC sweep. So we have to, with this depletion region has to respond to the gate to its maximum extent, and it has to respond, it will try to respond to this by not uh, saturating its depletion width, and it will try to move the above its maximum depletion width that it can achieve, because there has to be the charge balance that has to occur. So this curve 3 seems the only option that matches to our needs, because this, since this depletion width is not saturating as well, and these carriers also do not have the enough time to respond, so this curve 3 is the only reasonable option. And we will see how this in the upcoming problems, how we can see the different capacitances as well in the uh, in this MOSFET structure. Basically, when we will be having this large bias, we will be just taking the oxide capacitance, and when we are having this small frequency, small AC frequency, then the carriers will respond, and in that case, for the large bias of gate bias, we will be getting the oxide capacitance only in our capacitance calculations. But in case of this range between this, what we can say over here, in this region we will be having the semiconductor capacitance also that we need to take into the account for the low frequency cases.
Sir,
Now,
hello.
okay, yes.
Can you tell me, sir, what is this fast DC sweep?
Actually, if we have DC voltage on gate, we are incrementing it from, let's say, -1 volt to +5 volts. Let's say +5 volts might be much larger, or let's say 3 volts. So we are sweeping it in, when we are sweeping it slowly, we are sweeping it in units of or in steps of, like say, 0.05. So if it's 0, and afterwards the next DC pulse that we will be giving to the gate, it will be 0.05, and then it will be 0.1. We will proceed like that. But if it's fast DC sweep, we might go from 0 to 1 volt directly, and then 1 to 2 volts. That's what we mean by that.
Okay, sir. Thank you.
Okay. So let's move towards another problem, which says that we have some MOSFET with this p-type silicon substrate, where this is having the doping concentration of 3 into 10 raised power 16 per centimeter cube, and we have been given the work function for this to be equal to -1.13, and the intrinsic carrier concentration has to be taken to be equal to 1.5 into 10 to the power plus 10 per centimeter cube. Now in this case, we have been told to find the oxide thickness such that the threshold voltage is 0.65 0.65 volts, and we have been told to assume the thermal voltage to be equal to 25.9 millivolts. So let us do the potential balance that we know, and write down this equation for the threshold voltage. This threshold voltage, as I know you will also be knowing this same thing, this threshold voltage will be given by VFB, that is the flat band voltage. Let me not confuse you like that. Let me write down explicitly the terms, that is the phi ms, since and plus this phi f, this psi s, which in this case is 2 phi p. I have assumed the Fermi level pinning over here, plus q depletion maximum divided by this Cox. So let me see what quantities I have been given. 5 ms is there, and 25p I can find from the concentration, and q dep should be calculated using the uh, formula for this, using the depletion width formula. Okay, so we can get this maximum depletion charge first, and we know this Vt is given, this threshold voltage. Let me write it down as Vth, this V, so that we don't get confused with this thermal voltage Vt. So this is also given, this we know, this we can find. So let us find this q dep first. So this q dep, q can be, let me omit this subscripts, this will be given by q times Na x d, where this xd is the maximum, xd should be the maximum depletion width, maximum depletion width, and this will be 2 times epsilon s psi s, but this psi s I have assumed the Fermi level has been pinned to 2 phi f, 2 phi f p divided by q and a. So this is the depletion width. Now let me go back and find first this, now this phi fp, so that I can substitute it over here and get this depletion width first. Now to get this phi fp, uh, let me calculate it. Phi fp will be given by Vt, where this Vt is the thermal voltage, ln of Na by Ni, and this Vt is given to be equal to 25.9 into 10 raised power minus 3 ln of Na. This Na is 3 into 10 raised power 16, 3 into 10 raised power 16, and Ni is 1.5 into 10 raised power 10. So let us calculate these values. Ln of, so it comes out to be equal to 0.3577. So it is equal to phi fp is equal to 0.376. Let us take, let's round this off to 0.376. So this is phi fp, not phi f b. So this phi fp has been found. Let me put it in this expression to for this xd. So this xd, let me write it m, should be 2 times epsilon s is 11.7 into 8.85 into 10 raised power minus 14 into 2 phi fp. 2 phi fp is simply 2 into 0.376 divided by q and a. Q is 1.6 into 10 raised power minus 19, and Na is 10 to the power 16 multiplied by 3. So let us solve this expression. Let me solve this expression. 7, 105 into 2 into 0.376 divided by 3 divided by 1.6, it is 32.441, and the square root, so if I take the square root, it should come out to be equal to 0.1, it should come out to be equal to 18 into 10 raised power minus 6 centimeter. So if I have to convert this into meters, it will be equal to, this xtm will be equal to 0.18 micrometer, but in meters. But we will be mostly dealing with centimeters since our concentration is in the unit of what we can say, since it is in the units of centimeter cube. So xd has been found. Now I can find this charge for this Q, it will be given by Q times Na into XTm. It should be equal to 1.6 into 10 raised power minus 19 into 3 into 10 raised power 16, and this has been obtained to be equal to 0.18 micrometer, that is 0.18 into 10 raised power minus 4. So this has been obtained 0.18 into 10 raised power minus 4. Yes, this is correct. So if I now multiply these quantities, I should get it 1.6 into 3 into 1.8. It should give me 8.64 into 10 raised power minus 8 coulomb per centimeter square, since I'm dealing in per area. So this is the Q what I have obtained from the calculations. Now I can put this back in this VTH expression, where this VTH was given to be equal to, VTH is given to be equal to 0.65. This VTH is equal to 0.65. So I will write it down to be equal to 0.65 equal to 5 ms. 5 ms is given to be equal to minus 1.13 minus 1.13 plus 25fp is simply equal to 2 into 0.376. 2 into 0.376 plus this charge 8.64 into 10 raised power minus 8 divided by Cox. This is what Cox would look like. So let me take this expression and solve this by just taking 0.65 plus 1.13 minus of 2 times this 0.376, and it will come out to be 1.028 into epsilon ox by T ox, and this is equal to 8.64 into 10 raised power minus 8, or this is 1.028. This is epsilon ox. Epsilon ox will be equal to 3.9 is epsilon r relative for this relative, and this is the 8.85 into 10 raised power minus 14. This should be divided by 8.64 into 10 raised power minus 8 to get the thickness of this oxide. Now if I do the same, 1.028 into 3.9 into 8.85 divided by 8.64, it would give me this value to be equal to 4.11 into 10 to the power minus 6 centimeter. So let us check our options. 4.11, there is nothing like 4.11. Oh, it's in nanometer, so I have to convert this into nanometer. So I will simply say this 1 centimeter is equal to this, so it would imply 4.11 into 10 raised power minus 8 meter, doing just the unit conversion, or let us insert some slide. So it would be simply equal to 41.1 nanometer. So option B seems the closest option. It is 41 nanometer that we will be getting. Now there is another problem, and it shows that we have some capacitor versus voltage curve, and this curve has been given at some uh, uh, frequency, and that frequency is high frequency, and this capacitance values have been given to be equal to 7 picofarad and 1 picofarad. We have been told to find the depletion layer width in this capacitance in this, and also we have been given the area to look into this. Now if we consider this zero voltage, when it is at 0 volts, this capacitance, at that time there will be no depletion region. So this capacitance is solely and wholly given by this oxide capacitance. So oxide capacitance will be the only capacitance when we have this condition. So we can simply write this oxide capacitance C1 to be equal to 7 picofarad. Now, when this voltage has been applied, we don't know how much voltage, but there is some voltage, and this is a high frequency curve. The carriers will not get enough time to respond with this voltage, so they will there will be the depletion charge that will be the formation, that will be the result of that process, and there is this depletion region will result in the capacitance that will be associated with that, and that will be the semiconductor capacitance in that case. So that in that case, if we see this capacitance of 1 picofarad is the total capacitance in that case, when we are having this series combination of this oxide capacitance and the depletion capacitance. So this CT, which is equal to 1 picofarad, which is equal to 1 picofarad, is simply equal to 1 by CT is simply equal to 1 by C1, and let me write down this other capacitance 1 by C2. So if I write down this as CT, this CT will simply be equal to C1 C2 divided by C1 plus C2. Now the CT is 1 and C1 is 7. This is C2, this is 1 plus C2. So I will be getting this C2 to be equal to, this will be 6, and this will be C1 into C2, 7 plus C2. Okay, have I done something correct? Wrong. Yes, this is 7. This C1 is 7. This is 7 plus C2 equal to 7 C2, or this C2 is equal to 7 by 6 picofarad. 7 by 6 picofarad. Okay, now this is fine now, because the capacitance uh, uh, is much closer to the value of the one value. That's why I was getting confused, as this value would not have come close to 1, it would have come much less than 1. Since I know this is the reciprocal of these quantities, it should be less than the least of the 1 by C1, C1 and C2. This CT should be less than that number, and it should be close to the lesser number. So this is C2 has been calculated to be equal to 7 by 6 picofarad. Now let me add slide first and calculate the uh, since we have been given the area as well, that's good. So we can calculate the, what we have to calculate in this, we have to calculate the maximum depletion width. Okay, so I will simply write this C2 equal to epsilon naught epsilon R A by this maximum depletion width. Let me denote it by XD max. So we have been given the area, and these are the relative permittivity of, assume the relative permittivity of silicon and SiO2 are given. So we have to deal with this Si as this as silicon in this case, because we have to take the semiconductor. This depletion region will be formed in this semiconductor, so we will be taking this semiconductor permittivity. So this is silicon permittivity 10 to the power minus 12, and this epsilon r, this is multiplied in 8, and A is to be taken to be equal to 10 to the power of minus 4, and this is xd max, and this came out to be equal to uh, this came out to be equal to 1 second 7 by 6 into 10 raised power minus 12 picofarad. So this xt max is simply equal to 10 to the power minus 16 into 6 by 7 into 10 to the power of minus 12. So if I do 6 by 7, 6 by 7, it is simply 0.857. So it will be equal to 0.857 into 10 raised power minus 4 centimeter, or it can be written in micrometer as 0.857 micrometers. So let us check the options. It is the option B which is matching our calculations. So we will go with option B, that is 0.857 micrometer. So I think it's already 6, and if we do not have any further to discuss, we can close today's lecture.
No doubt, sir.
Okay, thank you. So I think we should end today's lecture.
Sir, one question.
Mhm.
Will the instructor will have an interactive session? Yes.
I don't know anything about that.
Okay.
I have no
Thank you,
information.
sir.
Sorry. You can ask them in the discussion forum. There is discussion
Okay.
forum. You can ask in
Yes,
there.
yes, sir.
Thank you.
Thank you, sir.